Hey guys, we're going to dive into the structure of the Earth, but first, let's start with a physical science review. Now remember that everything around us is composed of matter. Simply put, matter is anything that occupies space. Let's look at this first image. Everything in that photo is composed of matter. This matter, as we discussed during the formation of the universe unit way back when, is composed of elements such as, but not limited to, oxygen, carbon, nickel, iron, sodium, potassium, all sorts of elements. Now, this periodic table that I'm showing you here contains all the elements that have ever been discovered and is drawn to represent the common availability of these elements. So it looks pretty cool, right? These elements are made up of atoms, which contain subatomic particles such as protons, neutrons, and electrons. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Our protons and neutrons are composed of even smaller bits called quarks, if you remember. Simply put, the stuff around us can get more complex the smaller in size we go. Now, depending on how much energy matter possesses, it can exist in three states: solid, liquid, or gas. Some matter, like lightning or stars, exist in a fourth state called plasma, but we will disregard that for now. In all states of matter, the atoms are moving. Whether it be the chair you're sitting in, the air that you breathe, or the ice in your freezer, the atoms that make those substances are moving. Now, a solid consists of atoms that are densely packed together and maintain a defined shape. Based on their environment, these atoms do not have the energy necessary to separate from other atoms. These atoms are able to vibrate, but they do not separate from the other atoms. They have formed lattice bonds together. So think of like a grid. They're all interconnected together. Technically, all solids are considered frozen, just like when you think of an ice cube. And I'm not referring to the movie that I don't really like. Liquids are when atoms have more energy to separate from other atoms and melt. As a result of melting, the atoms can move freely and do not have a definite shape beyond where it's contained. Basically, liquids take the shape of their container. This is why we call atoms in a liquid state fluids. Liquids can go with the flow. Note that some liquids are more fluid than others. We call that property viscosity. Viscosity is a rate at which a fluid will flow and is determined by the atomic composition of the liquid. What the liquid is made of determines how fast or how slow that liquid moves. Finally, gases. Gases are also considered fluids, but the atoms have much more energy than liquids. Once the atoms have enough energy to get far away from other atoms, they are said to have become vaporized. Because of this ability to move quickly, many gases are invisible to the eye. Although some gases are colored, in order to protect ourselves from colorless and odorless combustible gases, we usually combine an unpleasant odorous gas like hydrogen sulfide to detect leaks. So like the gas that we have in our homes, we usually lace it with hydrogen sulfide, which smells like rotten eggs, to help cover that up. Now, atoms do not keep the energy they obtain. In fact, energy moves from areas of high energy to low energy. When gases lose energy, they go through a process called condensation. Likewise, when liquids lose energy, they freeze. Gases can also skip the condensation step and freeze too. This is called deposition and can be observed when water vapor in the air freezes from a quick drop in temperature. The inverse, where solids become gases, is called sublimation. An example of this is dry ice. Next, let's discuss how energy moves between matter. Focusing on the first images on the left, you can see that there are three types of energy transfer: conduction, radiation, and convection. Conduction is where energy is transferred through direct contact. Think of when you grab a hot pot and you burn your hand. When I worked in restaurants, I had many burns grabbing hot plates. You just never know when they get hot. They just put them under those hot lamps and you pick it up to put something on there and you burn yourself. Now, radiation is when energy is transferred via electromagnetic waves. Think of when you go camping and you feel the heat from a fire. You don't have to touch the fire to feel the energy. The energy actually comes from what's called infrared radiation. Heat lamps in restaurants, as I mentioned previously, use infrared bulbs, which then heat up the plates. Then through conduction, I burn my hand. Finally, there's convection. Convection is energy that's transferred through the mass motion of molecules. Typically, liquids or gases transfer energy this way, though some solids can do it too. These molecules will gather energy via conduction or radiation, and this excess energy excites the molecules to disperse, so they'll move out. Simply put, this is when something that is hot moves to an area that is cold. Hot to cold. If you take a look at the second image, you can see this gigantic sun. Now, this is certainly not drawn to scale. The sun isn't that big, but I think it gets the point across. When the light generated from the sun enters the earth, we have to remember we have more than just visible light. We obtain the entire electromagnetic spectrum: radio waves, microwaves, infrared, visible light, UV, X-ray, and gamma rays, all of which are generated from nuclear fusion inside the core of a sun. Although the atmosphere does a good job at protecting us from the X-rays and gamma rays, during the spring and summer months, we experience higher levels of UV, and the light from the sun exhibits a bluer hue. Those UV rays contain high energy, which hits the ground, causing it to warm up. This type of energy transfer is radiation, since the ground is warmed up by UV rays, which is from the electromagnetic spectrum. Once the ground heats up, the energy collected has to move somewhere. In this case, it moves to the air. The air is touching the ground, so it starts to gather the energy from the ground. Since the ground is actually touching the air, it is conduction. The air starts to take the energy gathered from the ground and begins warming up the air above it. In this case, it is convection. Convection spreads the energy around to surrounding molecules, and as the energy is transferred to cooler air molecules, the once hot and energized air molecules begin to sink back to the warm ground. This process is called a convection current. Maybe you've noticed when it's cold outside how the air feels real thick, and when you run outside, sometimes it's just tough to grab air. This air is deprived of energy, so since our bodies are warmed up, our warm bodies are transferring the heat to the air. Whereas when it's a nice day outside, say 70 degrees, the air feels thinner, but it's comfortable. This brings me to my next and final point regarding this chemistry review, and that's density. Density can be defined as the amount of mass per unit of volume. Take a look at this triangle at the top. It has the variables D for density, M for mass, and V for volume. If matter has a lot of mass, but little volume, it is said to be dense, and you will have a number typically that's greater than 1. And the inverse is true. Having little mass, but high volume, means matter is not dense. Typically, you will have a value less than 1, so typically like a decimal or something. This triangle will become in handy when you're trying to calculate density, mass, or volume. Just cover up the variable that you're searching for, and you can plug in the values you already have. More on that later. Maybe. Looking at this large image, you can see that the objects occupying the same space separate by density. If an object has high density or is very dense, it will gravitate towards the bottom. The objects that are less dense will occupy the space above the densest object. The ping pong ball will situate itself at the top. The reason is because the ping pong ball is mostly filled with air, which is also sitting on top of the liquids. The air is sitting on top of the liquids. Remember, gases are invisible. Basically, a simple way to understand how objects will occupy space based on density is by understanding how the object's atoms are arranged. If the atoms that make up the object are close together, the volume of the object is smaller, so it's denser. If the atoms are spaced far apart, the atoms occupy more volume, so it is less dense. This follows the equation we discussed at the beginning of this slide. Low volume means denser. High volume means not dense. Looking at the ice, water, and steam picture, we can get an idea of density as it pertains to the states of water. Water is unique in the sense that it can form something called a hydrogen bond. It's more like a pseudobond rather than a real bond. More so, it's a force that exists between water molecules because of their polar behavior, but that's for another lesson. These hydrogen bonds hold the molecules together, and when we draw them out, are displayed as a dashed line in between them. You can see that steam does not have any dashed lines. It's because we know that steam has a lot of energy. This energy allows the molecules to separate from the others and spread out. While this image doesn't demonstrate this separation, we have to assume it's there. On the other hand, ice, a solid, is experiencing hydrogen bonding, which occurs between the hydrogen and the electronegative oxygen. Solids do not have as much energy, so they must succumb to this intramolecular force. As you can see, ice forms this ring, which is part of a lattice structure. It's a lot of space. Because of this, ice actually has a larger volume. If I have a cup of ice water, the ice would situate itself on top of the water because of all the space between the atoms. This means of the three states of matter, for water, liquid water is actually the densest. That's not terribly common with many molecules, so that's what makes water pretty special. Now that's all for the Chem review. Hopefully that was a nice little refresher. Until next time.